Good morning, everyone. Welcome to our E3 2024. This is the fourth year we have this conference. E3 stands for Earth, Energy, and Environment. Uh, my name is Mohammed Solomon. I'm a professor at University of Houston. Uh, in addition to myself, I have two co-chairs with me, Dr. Professor Ben Ibn Haq, Emeritus Professor in Marietta College, and Dr. Ahmed Al Garhi, 10X Technologies. We have very strong and very detailed presentations today addressing various issues of energy. We have four keynote speakers and two panels. We have large number of people that register for the meeting, 2,600 people, professional and students, representing 200 different universities in 70 countries. So it's truly international program that we welcome you to it, and we hope you enjoy it. Dr. Ibn Haq, if you...
Thank you. I'm Ben Ibn Haq. As Dr. Solomon said, I'm recently retired professor emeritus and former chair of the Petroleum Engineering Department at Marietta College. And I basically just want to add my greetings to his and hope that everyone is able to get good benefit from these talks today, that we're fortunate to have such excellent speakers. And I think it's on a set of important topics. So I, with no further ado, would like to simply add my welcome and let us get on with the program itself. Thank you.
And now, good morning, good afternoon, and good evening for everybody who's tuning in. And a very warm welcome to the conference, the virtual space where ideas meet innovation and students from all over come together to ignite conversation that will shape tomorrow. We are beyond excited to have you here today as part of this incredible community of thinkers, dreamers, and future leaders. Whether you're joining us from across the globe, this conference is a platform for you to explore new ideas, exchange diverse perspectives, and build connection that will last long after the screen goes dark. Over the course of the day, you will be hearing from inspiring speakers, engaging in lively discussions, and diving deep into topics that challenge the status. So get ready to learn, share, and most importantly, be part of a movement that is focused on growth, innovation, and change. This is your conference where your voices matters, your ideas counts, and your participation is the key to making this experience unforgettable. Let's make today extraordinary. Let's get started. My name is Mayar Tore, a senior gas and petrochemicals engineering student at Alexandria University, and I'll be your moderator for today. So, as for kickoff, we have Dr. Meehan. Dr. Meehan is LF Peterson, 36th professor in the Harold Vance Department of Petroleum Engineering at Texas A&M University and a member of the National Academy of Engineering. He conducts research in carbon capture and storage, decommissioning of wells, and quantifying and decreasing emissions from oil and gas operations. He served as the 2016 president of the Society of Petroleum Engineers, SPE. Dr. Meehan holds degrees in physics from Georgia Tech, in petroleum engineering from the Oklahoma University as a master's degree, and a PhD from Stanford University. With more than 45 years of industry experience, he served on multiple industry boards, He has received numerous awards. Thank you so much, Dr. Meehan, for coming today. And the mic is yours.
Great, good. I hope you can hear me okay. I'm here at Georgia Tech at the School of Earth and Atmospheric Sciences in the Ford Environmental Science Building, which may seem a little bit of an odd place for a petroleum engineering professor to be speaking from. But I'm here meeting with climate scientists and meteorologists and researchers in direct air capture as part of ongoing research in various areas. When you get asked to speak about the future of petroleum energy, it's a little bit of a daunting task because first, why would we even need to have such a talk? The fact is, petroleum has made such enormous contributions to the quality of life and to the things that we do and to, positive benefits. Why would there be any concern? Is it because we're running out? Well, no, we're not running out of oil anytime soon. Is it because it's getting harder to find? Well, yes and no, and maybe not particularly. Technological advances for deep water as well as unconventionals have and are leading to increases in resources. And you're going to see a little later on, supply is going to outstrip demand for quite some time. The reason that we have this discussion is because of external pressures to use less petroleum because of climate issues. And I'm going to speak for the first part about that for a little bit of drivers. And I thought it was interesting. I asked one of my friendly AI generative things to give me a transition series of slides on the topic, the future of petroleum engineering and petroleum energy. And here's what it gave me. Here's slide 1 and slide 2 and slide 3 and slide 4. I hope that wasn't too fast, but you can see at least this particular AI model had a rather abysmal view of the future of petroleum energy. And I certainly don't share that view. Then I prompted it with a little bit of additional stuff. I said, give me something a little more upbeat about what the future could be, a little more sustainable thing. And I kind of got this one. So I'll use this as my topic title. And I am going to go through a few climate issues and talk a little bit about some of these drivers and keep those in mind for the context of where we're going. And apologize, there's a few blank slides in here. So we have first a pop quiz. And I'm going to make this pop quiz easy because I will give you the answers. And these are the answers. And so the questions, the first one is, what has been the temperature increase in degrees C since the industrial era began? Sort of 1.2 is that answer. And what is the current, target that we want to try to minimize? Well, it had been 1.5. I don't think anyone seriously believes we're going to limit temperature increase to 1.5. Sort of today's target is 2. And so how much? The answer is 800. And the question is, how many gigatons of CO2 could we add to the atmosphere and limit temperature rise to 2 degrees? And that answer, different models have different estimates, but typically it's about 800 gigatons. And so 44 is the answer. And the question is, how many gigatons per year of CO2 equivalent greenhouse gas emissions are we putting into the atmosphere? And so less than 20 is the what happens when you divide 800 by 44, So we have less than 20 years worth of time at our current emissions rate before we would get to this 2 degrees C. Now, I'm going to talk a little bit about the reliability of some of these models in a minute, but the answer that most of the climate scientists I speak with in almost all the universities and research organizations, everyone seems pretty confident that global warming is occurring, and it's been driven principally by anthropogenic CO2 and methane emissions. And no one particularly argues this point anymore. One of the concerns we have, this is a NASA analysis of land temperatures, and it's a little movie, so I'm going to play it here. And what this shows you, these are temperature anomalies. So in other words, how much do they vary from historical things? Because you can't get one temperature for the planet. But what you see is over time, yes, the temperature appears to be rising, but I'd like you to look at that tail on the right side. There's an asymmetric distribution of these temperatures. And what we're seeing is that the increase of very high temperatures is greater than it was in the past. So we're not just seeing higher average temperatures, but larger portions of areas that have very high temperature increases. So these are the ones that actually are the most problematic, particularly for human health. I'll give you a couple other just examples that I find interesting. Well, let's go on to the next one. On the top right is a map of a mountain range in Peru. And in the 1980s, a group of scientists on some of these mountains made very careful analysis of all the bird species as a function of their altitude. And it turned out that the higher you went up the mountain, the bird species changed. And just in the time period since then, the temperature rise has only been about 0.2 to 0.4 C, depending on where you are. But they've repeated this study and found that locally those bird species were found at higher elevations. They had moved up because the temperatures had changed. And 3 of 4 of the bird species at the top of these mountains were locally extinct. Now, presumably, they flew off to a higher peak somewhere else. They didn't go entirely extinct. But this elevator to extinction phenomenon has actually been seen multiple places. This is the HMS Challenger, which set sail on a scientific expedition in the 19th century and collected species of plant life and animal life and different things from around the world, including these foraminifera, which you could go out and see today at a museum in London. And foraminifera are these calcareous little critters here, and they're highly diverse, and they're an important part of the ocean lifestyle. And if you go and compare today those Challenger species with identical ones from recent species, you can see very consistent thinning of the calcareous structures associated with the decreasing pHs and other environmental impacts. And so these are happening over very long time frames, but are significant. And so what you're eventually seeing is a loss of certain species and increased dominance of others. This is sort of a natural evolutionary thing, but this one has at least some component of it driven by climate issues. It's not just obscure plants and birds and things that are seeing the impact of climate change. We're seeing warmer summer temperatures, and the problems that we have health-wise in certain areas are largely associated with nighttime high temperatures. So while in the daytime we get it obviously gets very hot, if it doesn't cool off at night enough, that's where heat-related illnesses and deaths increase. So we're starting to see that as a consistent thing, but we don't see it consistently across every country, or sorry, every city. What we see is that in areas like in the top right, where you have a lot of cement and not that many trees and lakes and parks, you see much higher temperatures. This is Baltimore, Maryland. And you can see on the left-hand side these green areas versus the red urban heat islands, as they're referred to. We see as much as 9 degrees F differences between nighttime high temperatures and comparable numbers for daytime high temperatures. Now, there is a kind of a social equity and fairness issue here as well. I won't need to ask you this, but where do you think the poorest people live? In the areas with lots of cement and no trees and parks and lakes, or out in the suburbs where they have the beautiful trees and forests and so forth? We all know the answer to that. And so what we're seeing locally in the United States and other large cities, as well as globally around the world, every example is almost consistently poorer countries and poorer residents in a given country are going to be impacted more by climate than wealthier countries and wealthier people in individual cities. This should not be a shock to anyone, but it's a serious concern. And the poorer people tend to have less political clout and ability to influence decisions. Now, before we get to this water flooding analogy, I want to talk with you about something I just chatted this morning. I was talking to this professor, and I said, I visited Canada back in the 1970s, and I went up into a resort area in the mountains, and I could see a glacier not too far up the mountain. And they had photographs on the walls from the late 1800s when this particular resort was built. And the glaciers were right there at they built this thing right at the edge of the glacier. So between the late 1800s and 1975, this glacier had gone up the hill. And I went back there just a couple of years ago, and the glacier has completely disappeared, at least from the resort. So clearly there are drivers other than climate that are changing some of these things that people blame on climate change. And he actually went through and explained this to me. It turns out that mountain glaciers, there are quite a few drivers for those, and it's a really well-solved problem, and people really understand why those glaciers have retreated. But the most important thing I learned was that if you added up all the glaciers in the world and melted them all, then you might get a meter of sea level rise. Whereas if you melted Greenland, it would be more like 7 or 8 meters of sea level rise. And if you melted Antarctica, which no one in any world is talking about Iceland being melting away. We're just talking about things at the periphery. It would be more like 80 meters. So the scale of these mountain things is different. So the complexity of the nature of these models is really high. So people talk about Greenland and Iceland and Antarctica and the things. He explained how you modeled uh, ice flows and sort of things. And it was very complex. Turns out that uh, unlike some reservoir models, these ice sheets, they have a viscous solid flow that you have to model over very long times, hundreds of years. And I will try to speak up a little bit. Um, Hundreds of years. And those flows have to be over 1,000-kilometer range. And additionally, at some point when the stresses accumulate, fractures develop. And those are on hundreds of meter scales and happened in minutes or seconds. So you have to have this enormous time scale, enormous links, as well as model high resolution, high frequency things. So it's a very difficult challenge to model. And a lot of people complain to me, and early in my career, I used to think, well, this whole climate thing and trying to figure out how much CO2 emissions and methane emissions actually will impact us. That's a complicated modeling thing. And I know from my own experience that reservoir models can vary quite a bit in their predictions. And we often don't have high resolution answers. And I mentioned that to a meteorologist who was a big modeling guy. And he asked me he didn't know anything about reservoir models. He said, tell me about these models. And so I described modeling a water flood. And he said, okay, let me get this right. You get your mathematical equations and describe the porous media and the permeability and porosity and thickness and all these other properties. And you inject water, and then it displaces oil to various degrees. And eventually that water is produced at the producers, and the amount of water increases over time. Yes, that's pretty much it. He says, and so your different models have different times for them to break through and different rates at which they increase afterwards. Yes. But all your models show breakthrough, right? Yeah. And all of them show increases afterwards, right? Yeah. Says that's kind of where we are. In weather modeling, every model is showing that what the impacts of increased CO2 and methane are in the climate. How quickly they cause severe problems is varying. What we should do about it is varying, but nobody disagrees that it's happening. So that's kind of my answer. So the possible solutions we have are to mitigate, adapt, or suffer. And we're already doing some of each. Mitigation are those measures to reduce the magnitude and rate of climate change, at least that part caused by human activities. And there certainly are a component of climate change that are not caused by human activities. This is in the water flood. So we're going to improve the conformance, and we'll change the rates, and we'll reperforate. So we can change that pace and magnitude. Adaptation are measures to reduce the adverse impacts of human well-being from the climate things that do occur. So this is changing our separators at the end of the water flood. And suffering the impacts, of course, that's paying the higher operating expense. So we have the water flood analysis continue. Our goal is enough mitigation to avoid the unimaginable and enough adaptation to manage the unavoidable. So mitigation is largely affects petroleum engineers and people in the future users of petroleum. We need to increase efficiency. This is really critical. There will be a replacement of fossil fuels, particularly coal, with biomass, wind, solar, and nuclear. replacing fossil fuel powered transportation with electricity or potentially hydrogen for light duty vehicles. And for heavy duty vehicles, we've got to look at sustainable biofuels or hydrogen. For heavy duty transportation, aircraft, obviously sustainable aviation fuels. And CO2 can be an important part of that supply chain. The other ones that affect us, of course, equipping emitters with capture technology and storing or using the CO2 emissions that we create. And then decreasing or eliminating emissions in oil and gas production operations, monitoring those for fugitives, flares, venting, and there's a lot of opportunities to do that. In fact, the opportunities to decrease fugitive flares and venting is extremely high compared to today's carbon capture. We looked at what would just happen if you replaced all the pneumatic actuators with electric actuators in the Americas. And that would reduce CO2 emissions or CO2 equivalent emissions more than all of the carbon capture storage facilities in place today. So another aspect of mitigation is to increase sinks so that we have less net CO2 emissions. And clearly, some of those are biofuel related, but those almost all of the biofuels have issues that require carbon capture and storage. And finally, of course, direct air capture is one of those. And we're not really be talking about the details of carbon capture and storage much today, but or at least in my talk. I'll end this kind of discussion. No energy company will be unaffected by clean energy transitions. Every part needs to be considered, how we consider and what we do to respond. Doing nothing is not an option. Or as the t-shirt for the Stanford Petroleum Engineering or Earth Resources Engineering group says, there is no planet B. I threw this just as a humorous transition. Some of you know that that you sometimes see these people doing wind and solar and they kind of looking down their noses at us. But we are important to the total energy business. And I want to caution you about something. Every one of you has or will see some graph that is a measure of some measure of quality of life, GDP per capita, literacy, access to clean water, whatever it is, as a function of energy use. And so I want to show you a couple of things here. This is child mortality, the number of children that die between 0 and 5 years per 1,000 births, as a function of GDP per capita. And the green dot over here to the right is the United States. These are scaled based on their populations. The big red dot on the right is China. The big red dot in the middle is India. And you see that the child mortality rates in the US is something like 6. To give you an idea, that number 100 years ago was 130, which is higher than any of these countries today. Remarkable changes that have come about. But there are a lot of countries that have less GDP per capita than the United States and lower child mortality rates. So frequently you see a graph that looks something like this, so child mortality versus oil consumption. And sure enough, the countries with the lowest oil consumption have higher child mortality. But this correlation doesn't really hold up all that well. There are plenty of countries out here that use a lot of oil whose child mortality is not particularly low compared to the developed world, which is this group of bubbles you see here. These are primarily OECD countries. So going back previously, remember the real driver to improved quality of life is the wealthier countries. Wealthy countries have higher qualities of life. Surprise, surprise. They also use more electricity and they use more oil. It is not oil use or electric use that drives high quality of life. It's the wealthy countries, and there are a variety of reasons countries are wealthy. There's electricity generation as a function of GDP per capita. Clearly, wealthy countries use more and have more electricity. Electricity use is correlated with quality of life. For example, here's oil consumption versus GDP per capita, same thing. But it is not oil and electricity use that drives quality of life. It is the wealthy countries. Here's a cartoon. I used to think correlation implied causation. Then I took a statistics class. Now I don't. The other person says, sounds like the class had helped. Well, maybe. So now he's not going to assume causation. And so that's one thing you should look at when you see a lot of statistics that get presented and thrown your way. They're not necessarily causation. Let's move right on to today's topic because we've got a lot to do in just a little bit of time, and I want to add time for questions. This is primary energy today or recently, and you see that fossil fuels in primary energy, 80% of the world's primary energy. And then renewables, just a little less than that. Electricity generation, a lot more of the renewables driving electricity generation. And of course, crude oil at the bottom hardly drives any electricity generation, but natural gas and coal drive still very large parts of them. And then let's switch on to skip final consumption and CO2 emissions. Oil, coal, and natural gas are still the largest part of that. And of the world's greenhouse gas emissions, fossil fuels are the largest single part. And you can see coal is a very large part of it. Natural gas, I'm going to skip that slide. So I'm going to give you some conclusions. A combination of economic trajectories and increasing use of various energy saving technologies are going to slow the demand for growth for petroleum. How it will happen over the next few decades is hard to say, but in the next decade, demand growth, though, will keep production much higher than climate targets to get to 2 degrees C. Nothing we're doing now is getting us on the path to 2 degrees C. A huge rise in world supply outside of OPEC Plus is going to be driving demand. Much of that is from natural gas liquids and condensates. The biggest spare capacity producer will remain Saudi Arabia, and their capital is going to be expanding petrochemicals, NGLs, condensate use, because that's the largest demand growth sector. The demand growth for refined products is going to be displacing those NGLs and biofuels, especially to the degree that EVs, both BEVs and hybrids, displace transport fuels. So government policies around the world seem to be on track to fast track energy transition. Now, some of you may not have paid any attention, but yesterday, the American voters made a decision that could very well impact how much the U.S. fast tracks energy transition. And we're presuming at this point that it might be slowed, and at least some of the requirements might be slowed. I don't know about the incentives at this point. If you look at the spare crude capacity in OPEC Plus, we anticipate that that is going to continue to grow uh, pretty significantly. So, and that's partially because of big increases in U.S. conventionals, Guyana, Brazil, and a few other countries that have had uh, a lot of increased oil production outside of OPEC plus, plus natural gas production leading to a lot of additional NGLs and condensates. So the total supply capacity, we're looking at increasing by 6 million barrels a day, which will about 8 million barrels a day above demand. That would be a challenge for OPEC plus. They have a plan to decrease their voluntary cuts, but that big a cushion would make it difficult for them to do that because of the impact on prices. Prices could go down significantly if they didn't continue those cuts. And so a lower price for oil could be pretty challenging for the U.S. shale industry, depending upon how low it goes. So we're looking at global oil demand almost 100. It's almost 105 million barrels a day, basically staying at this level for the next 5 or 6 years. So the big gains, Guyana, Brazil, Canada, and Argentina coming on. The growth in world oil products demands, we're looking at decreased gasoline demand, but increased naphtha, LPG, and ethane. Now, LPG and ethane are principally used for plastics. Naphtha, of course, those of you, if you, that's a oil product, and it's widely used in plastics as well. So the big demand for solid uses of oil. One benefit of that, although people are opposed to plastics for a variety of reasons, one benefit of that is the CO2 from a barrel of crude. The more you use in plastics, the less you emit to the atmosphere. Most of the oil barrel is still burned ultimately. So this is where we think the changes will be. And the gray curve here that starts up here and declines, this is on the right-hand scale. This is the percentage of oil used by OECD countries. This Organization of Economic Cooperation and Development. This is the Western, the large economic powers, and that I expect their percentage to continue to decline. In fact, the absolute amount of oil used by OECD countries is likely to decline slightly, whereas non-OECD oil consumption and use will continue to grow, and that will be the driver for essentially all the demand. And we'll look specifically at India and China. Some of the drivers for that, if you go look, here's the United States. The GDP in the U.S. has continued to grow. You see COVID right here. Whereas the vehicle miles traveled, while they dropped in COVID as well, they're continuing to increase, but gasoline demand is going down, in part because of the increased number of electric vehicles. And so if you look at the oil demand displaced by electric vehicles, right now it's just under 1.5 million barrels a day. And that's comparable to, that's just twice as much as the oil demand decrease because of telecommuting. But the forecast here up to 2030, we're looking at something like 6, and some people have this number up over 7 million barrels a day displaced by EVs by the end of the century. And 2030 is not that far away. Air transportation is another big use of liquid hydrocarbons. Ignoring COVID down here, the red curve at the top, this is the 2024 numbers. And what you see here is record amount of oil used in air travel every day. A lot of pressure on them to use more sustainable fuels. In Saudi and a few other countries, people have in the past burned crude oil, fuel oil, gas oil for electric power generation. That has continued almost at the current levels, changed the countries a little bit, but we are anticipating a pretty significant demand as natural gas begins to take up the slack there. So that will also result in increased oil availability. If you look briefly at China, on the top right, you can see that demand curve is very much like what we saw previously for the global answer, and that's because they are driving that answer. Although their GDP growth continues to look pretty good, we're looking at oil demand dropping off, particularly non-petrochemical oil demand. So if we move ahead to India here, India is the exception to this thing about a decrease in demand for gasoline. India will lead the global demand growth, more than all of Africa at this point as the estimate, especially for road transport fuels. India has become the largest economy, largest population in the world, still far from the largest economy. If you look at their passenger cars, that's expected to rise, from today's level of about 50 million cars to nearly 70 million cars by the end of the decade. And some of those will be EVs, but the large number of 2 and 3 wheelers, the growth in those will be from something like 250 million to 310 million. So adding 60 million of those, the majority of which of the incremental ones will be EVs, or a large portion of them will. So this is certainly the fastest growing economy, and we'll look at India. India's CO2 emissions are going to rise very substantially over the next decade. And when you see these graphs of emissions by country, India's is going to rise significantly. They still use a lot of coal, probably building more coal plants now than China's building. And so they're going to be a very energy hungry country associated with improving quality of life for this enormous population. So if you look at where that oil demand is by region, China, India, and the rest of Asia is where the demand will be. To a lesser extent, Africa, the OECD countries, oil demand goes down. I'm going to show you a scary graph here, and we'll go to questions pretty shortly. The scary part of this graph is this is the BP oil forecast for the current trajectory in green, what they expect to happen. And that's 105 million barrels a day or so in 2030, about where I've been talking about. And their forecast as a result of everything else. The current trajectory, just under 80 million barrels a day by the end of 2050. OECD is the Organization of Economic Cooperation and Development. So it's going to be the US, Canada, most of the European countries, and so forth. So these are the developed countries. And so this forecast, this green forecast for current trajectory, you could draw another one of these that goes up slightly and ends up at 110. And most of the forecasts of the current trajectory will be in that range. But if you look at what it would take to get to net zero emissions, coupled with all the other carbon capture and solar and wind forecasts, et cetera, to get to net zero, that number would have to drop to 30 million barrels a day by 2050. And coupled with that, essentially all of the coal plants in the world would have to be shuttered, including some that are currently under construction. So the possibility of getting us to net zero is net zero. I think we're going to have a difficult time achieving those climate goals. And So I think it behooves us to focus on where we can do the most impact for the dollar and be as efficient and reducing CO2 and methane emissions as we possibly can, and still deliver the oil and gas required for the world. Just a few more slides and we'll go to questions. Actually, I'm going to go ahead and skip the rest of these slides and go to the conclusions. Implications for petroleum engineering students. Oil and gas demand growth in the next decade is going to be fine and support significant demand for petroleum engineers. Over the long term, I don't know. If countries change and continue to focus and do the radical things that would be required to decrease global demand for oil and gas, well, or let's say oil, because natural gas demand is not going to go down anytime soon. That's a very expensive proposition and very difficult to accomplish. So I'm not sure what that forecast will be, but I am much more bullish over the next decade than I am long term. It's just too difficult to make that forecast. Now, I'm going to end with sharing now. And so switch back over so I can answer some questions.
Thank you. Thank you so much, Doctor, for this informative session. And for the Q&A session, the first question, is it possible to reuse the emitted gas or reserve it for reuse?
Is it possible to use the emitted gas or CO2?
No, or reserve it for reuse.
Are we talking about CO2 or emitted? Let me just address both for there's a big gas monetization problem in a lot of countries where we're flaring or venting, and there are economic and technological opportunities to capture or reduce almost all of that. The economics might require subsidies or discounts or challenges to make that happen in certain places. But one of my big concerns is Nigeria, and I think there are a lot of opportunities there to decrease their emissions. Some areas like Russia do not apparently care much as a country about those large numbers of emissions. And the absolute largest amount of flaring and venting in the world is in Russia now. So the large amounts per MCF, happening in Iran and Iraq. But if you're talking about CO2 emissions, there are certainly ways to capture CO2 both from natural gas and from industrial processes. It's fairly expensive to do so, and it's largely a function of the concentration. So if you're at an ethanol plant where the emissions are like 90+%, it's essentially a dehydration process. If you're at an ammonia plant where it might be 40%, there's a certain amount of energy required to extract that CO2. And at combined cycle natural gas power plant where it might be 4 or 5% CO2, there's more energy required. So there's a significant cost. But let's go ahead and go on to the next question.
Are wheel exhaust filters an effective solution for reducing high pollution levels?
I'm sorry. Can you say it? Why don't you give me the time that question came in so I can look it up and read it? I'm having a hard time hearing you.
I don't know.
In the chat, the times show up with the questions.
Okay.
Okay,
I will write it.
Okay, so I see one question. why is smog spreading everywhere, mostly in India and Pakistan? Well, I rode in the train once from Calcutta to, is it Dhanbad? Is that where uh, the old ISM is? It was ISM when I went, and people burn raw coal in Pakistan and India, and they don't have uh, small controls, and they burn a very low quality coal. So that's the driver there. Uh, and so let's see, for CO2, why do you think the best and less expensive way for carbon capture is? Clearly um, the way that's most widely used are absorbents, particularly amines of different types, but a ton of money in research is going into solid adsorbents, uh, membrane technologies, cryogenics, chemical looping, such and calcium looping, and inherent capture technologies. I particularly like two of those. One is the use of metal organic frameworks uh, and because I think those are some really good opportunities to improve the efficiency of capture, decrease the loss of product during the capture process, and use less energy to regenerate the project. So another thing is in like amines, they tend to have a very high capture rate early and then lower and lower capture rate as the CO2 concentrate goes up. MOFs, at least at the lab scale, tend to have a little more constant capture rate. The inherent technologies where we separate oxygen from the air first and use oxygen in the process, whether it's electric power generation or biofuels or whatever the industrial process is. The result of that is the emissions are almost pure CO2. So, um, uh, and so that answers one. And let's see, what is your perspective on the reservoir exploration discipline's potential to apply CCUS in the near future? Clearly, that's a huge focus for of a lot of us in the business. Most of us tend to focus on the storage aspect of that. The big cost savings are going to come in the capture space. One of the biggest challenges, at least in North America and Europe, is enormous opposition to pipelines. So that's going to be a big issue there. I Do you think basalts are a promising element for carbon storage? So the reason this question was asked is basalts and a few other rocks adsorb and trap CO2 permanently. And they do so not immediately, but relatively quickly. So most of the underground reservoirs that we're doing carbon capture and storage in now are first enhanced oil recovery. That's the vast majority of them. We don't have enough EOR projects to capture all to store all the CO2 we're going to use that we're going to generate, and they're located a long way from a lot of the CO2 emitters. Saline aquifers is where most of the new projects are focused. The biggest problem with saline aquifers is that the pore space is already full of a slightly compressible fluid. And so as you inject dense phase CO2, you will increase the pressures and resultant stresses. And they will likely be triggering some fault movement and some potential migration over time. We don't typically characterize saline aquifers as well as we do oil and gas fields because we don't just drill a whole lot of wells in them because it's just salt water. And so if you do this near population centers, even if the earthquakes are too small to be felt at the surface or to do any damage, people are going to be opposed to earthquakes, and that's going to be a problematic challenge potentially. The use of saline aquifers more like an area where the Gulf Coast with softer rocks or more benign stress environments might be more attractive than hard rocks and higher stress environments. The third area is depleted oil and gas fields. And unfortunately, depleted gas fields have some potential there, but depleted oil and gas fields have two big problems. One is that there's a ton of wellbores through those, and they all are potential leakage paths. And so, we pay people to store CO2, not to have it leak into shallower areas, potentially to the atmosphere, but also more likely to shallower aquifers, and some of those might be groundwater. That's a concern there. The other concern is that in the very good oil fields, they are porous and permeable and laterally continuous. And if you look at any oil field that has those three characteristics, we tend to water flood them, or they have very strong water drives to begin. Regardless, at the end of their lives, they are full of slightly compressible fluids, just like the saline aquifers. I don't know how many more of these I have time for, but all right. Thank you for the opportunity.
Thank you
Best of luck.
so much for coming today.
Cheers.